Good morning or good afternoon everyone, I hope you're doing well. This is Carl speaking and this will be Practical 1 Part 1. On behalf of Mr. van der Bank, this video will serve the purposes of just reducing the length of the original video made by Mr. van der Bank in class, and specifically this video will only focus on how to do the calculations for these 7 things down here. Alright, so let's get right into it. This is Practical 1, Evaluating Utility, and it's Part 1, Quality of Decisions, as you know, hits and misses. So some important abbreviations before we get started. FN refers to false negatives, TP refers to true positives, FP refers to false positives, and TN refers to true negatives. The nature of these things we'll get into as we go along the 7 questions, but for now we're just going to go over the little case study and all of our beginning information. You can see that the dataset for the tutorial is available on Sunlearn, quality.xlsx. The dataset includes 4 variables, which are the case numbers, the criterion in rands, x1 predictor 1 and x2 predictor 2. Alright, so here we've got a case study. You'll see that I made use of different colors. The green refers to the criterion, blue to the predictors, purple to the cutoff score for the criterion, and light blue, grey is the cutoff score for the predictors. Alright, so this data set includes the criterion, which we know is this one here in rands, and test performance, which are these 2 predictors, our sales consultants at ads 24 that were collected during a validation study. The criterion value represents the monetary value of advertisement space sold by each sales consultant. Sales consultants are required to achieve a target of at least 60,000 to be considered minimally acceptable in their role. Each sales consultant was tested on 2 different employment tests. The cutoff score used for both tests are 15. Management has requested that you evaluate the quality of decisions that can be expected using the 2 tests. So the following calculations and analysis are required. We see here there are 7, and this video will aim to address these 7 questions as accurately and as concisely as possible. Question 1. Calculate the correlations between the criterion and 2 predictors and interpret the values in terms of percentages explained. Alright, so I'm going to take us over to the Excel spreadsheet where we will be doing all our calculations. Again, as is the same with Practical 2, please don't be too concerned if you do not have all the values as we have here, but know that by the end of this video you will have all the values that you need. Alright, so going over to the Excel thing here, we can see a lot of values, most of which is not important for us right now. Our focus is strictly here on the correlation calculations. So they want us to determine the correlation between the criterion, which is y1, and the predictors, which is x1 and x2. So in order to calculate this, we use the formula equals correl, and then we're going to make use of our data series, always knowing that the first is always our dependent variable or criterion variable, and the second is our predictor or our independent variable. Right, so we choose the data series all the way up from B2, which is here, down to B101. So we can deduce that there are 100 observations. And we make use of the same for x1. So when we get this value, we see that it is 0.4039, blah, 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 blah. And then just to simplify it into a percentage for us, we can take this amount that we got here, which is G3 times 100. And this will give us a percentage of 40%, 0.4. And then when we do the same, we say equals correl, again making use of our criterion variable, and this one being our predictor variable. And this, once we do that, we'll get 0.8012, blah, 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 blah. And then doing the same here, timesing this to take this value and times it with 100, we get 80.13 percentage. So the second part of the question says to interpret the values in terms of percentages explained. So here we can see that for the first one, we see that the correlation between y1 and x1 is only 40%. This means that 40% of the times, one can interpret it as being 40% of the times it will be accurate, or for each time that we do see the correlation between 1 and 1, we see that there's a 40% chance of it being accurate. We can see that this is fairly low, in contrast to the 80% correlation that we have between y1, as we can see here, y1 and x2. Alright, so 80% correlation is a lot stronger than 40%, and again it means that 80% of the time the relationship between x2 and y1 is accurate. Alright, this concludes question number 1. Question 2. Create a scatter plot for each of the predictors with a reference line on the x-axis to indicate the test cutoff score and a reference line on the y-axis to indicate the minimal acceptable criterion value. Based on this scatter plot, how effective would you say the current procedure is, and compare the two predictors in this regard. So we can see here there are multiple levels to this question. The first being to create a scatter plot for each of the predictors. So there will be 2 scatter plots because we've got 2 predictors. The second part is to include reference lines on the x-axis and y-axis to indicate the cutoff scores and minimal acceptable performance. And then thirdly, we need to interpret this. Alright, so when we go over to Excel, you'll see that I already have the scatter plots here in preparation for this video, but I'm going to show you guys how to do it as well. Alright, so just make sure before we get started, you'll see that we have chart title, we have vertical and horizontal axis titles. We do have the reference lines put in here at 15 and at 600,000, and we have it for both x1 and y1 as well as y1 and x2. Alright, so how do we do this? We say insert. We want to choose our chart type, which is a scatter plot in this one. We want to go here. Alright, now we need to select the data for our chart. We want to add here. We want to make the series name scatter plot x1 y1 or whatever you prefer. The series x values will be the first predictor, and the y values, after we take this back just to make sure that it's only an equal sign, will be our y values. And remember, if you want to take it down quickly, it's Control Shift down. Alright, there we go, that concludes everything. We say OK, and here we go, we've got our basic scatter plot, some already with the chart title included. Alright, but now we need to put in reference lines. So in order to do that, we're going to go, we need to make sure that our reference lines start at 15 and 0 and go up to 15 and 100,000, which is why we make use of this little column here, because we're going to be putting this in as a different dollar series altogether. So you'll see reference line of x, it starts at x15, y0, and it ends at x15 but y 100,000, which is the top point of our data range. So what we want to do is we want to go here to data, we want to select our data, we want to add, we want to say this is a reference line on the x-axis, we select our x values, which are these 2, we select our y values after erasing that, which are these 2, we say OK, we say OK again, and now we see we have our reference line here. In order to make it a line, we simply go here to our format data series thing, and we want to make sure that it says solid line. Alright, we do the same for the y-axis. So here we see that it starts at x0, y 60,000, and it ends at x25, y 60,000. You see? So we put in this one here for reference line y. We go to our figure, we add data, we select data, we add, we want to make this one say reference line y, selecting the x values, which are these 2, and selecting the y values after we erase that, which are these 2. And we say OK, and this creates us this one, give it a solid line, and there we go. We've got the reference lines. Alright, so now we get to the little extra part just to make sure that it looks neat. We go here. Alright, so this part is optional, as I don't think we'll be getting too much marks simply on the aesthetics of our model. I think the most important thing is just to be able to put in these reference lines and the scatter plot. So this part after this I would think is optional, but perhaps just have a look at it anyway and see if you want to include it in your exam. Alright, so in order for us to tidy it up a little bit and so that it looks nice and presentable, we want to do the chart title, we want to have the x and y axes, or the y axis and the x axis labels, and we also want to limit these 2 down a little bit so that we can eliminate this white space here. Alright, so let's start when we say here with our chart elements. We want to have the chart title. We want to have axis titles as well. So then we simply put it in here, scatter plot y1 x1, and here we put in y1 and x1. Alright, then once we've done that, we want to make sure that we eliminate these little white spaces. So we click on the y-axis, we go up here to the right with these data or these axis options, and we want to just expand this this thing here, and we want to make the maximum value 100,000. It might differ depending on the value, but you will see of your data series, but you will see now it looks nice and concise for this one. We do the same principle here, and so where it's now is maximum of 30, we only want it to go up to 25, and there we are. Now we've basically got a duplicate of this. This little line comes in later on in the question, so we don't have to be concerned too much about this. You can duplicate this process for the scatter plot of y1 and x2, basically by following the steps we just did, but just to refresh a little bit. So we're going to create a scatter plot here somewhere, wherever suits you best. We're going to input our data into it, which will be y1 down to x2. We're going to want to also again put in our reference lines, which are the exact same two here, which is adding the data and adding them as well. We want to make them solid lines, and then thereafter we want to just tidy up our figures a little bit. So we want to make sure that there's a chart title, axis titles, and that we do not have too much white space. So we want to make sure that these represent our top values of 100,000 and 25. Alright, this concludes the practical part for question 2, but now we still need to interpret the rest. Alright, the second part of this question asks us, based on the scatter plots, how effective would you say the current procedure is? Compare the two predictors in this regard. So when we're looking at our scatter plots, what do we want to consider? Well, firstly, we want to see how does the spread of the data look. So you see here for x1 we've got a very large spread, no clear pattern. If we ignore this, there's no real clear pattern evident, whereas with x2 we can see that it has a very solid upward movement, a positive relationship. So as the one increases, the other one also increases, but here we see it's very difficult to determine this as easily as it is here. The second thing we need in order to interpret these values is to understand in context what these four terms refer to. So we have false negatives, true positives, false positives, and true negatives. So basically, if we want to divide these four into our quadrants, our scores, we can see that false negatives are those that were equal to or above 60,000, but that were smaller than 15. Right? So we see it's the first quadrant here. And false negatives basically means that the person's score on the X predictor was lower than 15, but their actual performance was above 60,000, which is the minimal acceptable performance for the criterion. So we see that it's a false negative. It was erroneously labeled as negative. Then we have true positives, which are values that are above 60,000 and also above 15, equal to or above 15, which is our second quadrant over here. Alright? True positives basically means that the person's minimal acceptable performance does lie equal to or above 600,000, but also above 15 or equal to 15 on the predictor. Then we have false positives, which are those ones where we say the person scored less than 60 or 600,000, but they had a score of greater than 15 on the predictor, which will mean it's this quarter here. And then true negatives are people that scored below 60,000 and also below 15. In other words, those are the candidates most likely to be rejected, and so we can infer from this data that this one quadrant here, quadrant number 4, and quadrant number 2 are our ideal states, because we want to make sure that people who score below 60,000 or people who have a performance of lower than 600,000 and a score of lower than 15 should not be selected, and we want to make sure that people who have a score higher than 15 with a minimal acceptable performance of 600,000 or more, which is here, are selected. Alright, so based on these values we can see that here the spread between these two quadrants, here there are a lot of values in those two negative columns, and then here we see there are not so many here. So for example, no one who scored, we can almost conclude that no one who scored higher than 15 got less than 600,000, meaning it's very accurate. And we see here that the most of the scores fall in our 2 quadrants that we want. Alright, so basically what we can conclude is this one for the scatter plot for y1 x2, which is our second predictor here, is more accurate than is the one for x1. This concludes this question. Question 3. Create categories in the dataset representing the different decision outcomes and calculate the number of cases within each category. In essence, we have false negatives, true positives, false positives, and true negatives. Taking us over to the spreadsheet, just to remind ourselves, false negatives are the ones that fall here, true positives fall here, false positives fall here, and true negatives fall here. If you're confused as to how we know this, just refer to earlier in the video. Alright, so the formulas that we'll be using is count ifs. We want to make sure that it is ifs and not just if, in that we're going to be using multiple criteria. Right, so how do we do this formula? The first part is selecting the criteria range, which is for our criterion variable. So we start off with the first value and we end off at the last one. Then the second part of this formula is to choose the criteria, which is within inverted commas. And we see that for true false negatives, we want values that are higher than or equal to 60,000, but that are smaller than 15. You will see here in the second criteria. So we got this. Right? So the first thing is we only want values that are higher than 60,000. Then we choose our second criteria range, which is x1, and the criteria for that range, it must be less than 15. And this gives us our false negatives. Then for true positives, we want values that are above 60,000 and above 15. Right? So then we make use of this formula, inverted commas, greater than or equals to 60,000, and we see here greater than or equals to 15. Alright, then we go on, we see there are 13 instances. We look at false positives. These are values that are below 60,000, right, but that they are greater than or equals to 15. So we want these ones here. So we see that there are 11 instances in this case. And then finally we look at true negatives, which is this quadrant here, meaning it is values that are less than 60,000 but also less than 15. Alright, so then if you want to just do a little quality check, we can say equals sum, which just counts all of these things together, these four, and just to make sure that it comes up to 100 as we have 100 participants, we see that it does. Alright, then we can duplicate this process for x2, where we simply, the only thing that changes from x1 to x2 is our data series. So all the other things remain the same. So if we want to do it a little bit quicker, what we can do is we can simply copy over, we do the first one, we copy over this formula as such. Right, we go here, we copy it in there, and now all we want to change is just this data series, which we want to be x2. Right, there we go. Right, so we see there are 15 instances, which is correct. So the only thing that changes between here and here is just that this changes to D2. So you can actually copy over all of these. If I may just quickly demonstrate, copy this one over to here. We want to take this one, copy it over to here. We want to make use of this one, copy it over, press escape, go down here, press Ctrl V or paste. Alright, and now we just want to make sure that the data ranges are correct. So we want to change this to D2 all the way down to D101. We want to do the same here. D, enter. Lastly, D, enter. Alright, again doing sum just to make sure that is correct. This concludes question number 3. Just to take you back there if you want to have a look. There are the formulas. The most important thing regarding these formulas is not necessarily being able to duplicate this, but understanding where it comes from. Question number 4. Use the following ratios as indicator of the quality of decision making and compare the two predictors in terms of the ratios. So they want us to look at the overall quality of decisions, which is our true positives and true negatives, divided by the entirety of options that we have available. And we also want to look at the success ratio in terms of Taylor-Russell, which is our true positives divided by the true positives plus the FP, which is our false positives. Alright, so when we go over to Excel, we can very easily do these calculations here. So upon completing these, we are able to do this. When we look at overall quality of decisions, we know that it is true positives plus true negatives divided by all of them put together, and we want to times it by 100 to get it into a percentage, right? So in this case we see G8, which is here, true positives plus true negatives divided by brackets G7, which is here, plus end brackets times 100. You can do the same here for the overall quality of decisions for X2. We again just take these values now, and we see the true positives plus the true negatives in brackets divided by them all. So we say G14, which is false negatives, plus true positives, plus false positives, and finally plus the true negatives, everything in brackets times 100 for percentage. Alright, so that's the overall quality of decisions. Then when we look at success ratio, which is the true positives divided by the true positives plus the false positives. Alright, so basically we see that it is true positives divided by true positives plus false positives, and to get it into a bit more of a percentage or a rounded number, we times it with 100. You can duplicate this process for the success ratio of X2, where we say true positives, which is here, and we say divided by true positives plus false positives times 100. We see 80. Alright, so that's the first part of this question. Now we need to compare the two predictors in terms of the ratio. Right, so when we look at this, it becomes quite evident that the overall quality of decisions for X2 is somewhat higher than it is for X1, but we can see that it is much higher for X2 in terms of the success ratio than it is for X1. So basically, what does this mean? When we look at the overall quality of decision, we know that we ultimately want the true positives and the true negatives as much as possible. As you can see here, X2 being the better model, we want most of our values to be in this quadrant and in this quadrant, because that will mean that the test is accurately measuring what it is supposed to measure. Because if a person scores less than 15, they should also have a performance of less than 60,000. And vice versa, if they score more than 15, they should have a score of higher than 60,000. Alright? So we say overall quality decisions is the best or ideal scenario divided by the totality of it. In other words, what we're saying with the overall quality of decision is 71% of the times for X1, the test will accurately predict whether the person goes here or here. And then the same applies for X2, overall quality of decisions, 81% of the times the values will either fall here or here. Alright, then looking at success ratio, which we see as true positives divided by true positives and false positives. Basically what we want to see is, out of every instance, what is the chances of a person going through based on them having the right score, but also being above 60,000. So we see that the success ratio for X1 is much lower, with only 51%. This means that of the people that go through, only about 54% of those are people that actually did do 15 or above and 60,000 score here. But then we see that there, in contrast, the success ratio for X2, which is in this case 80%, is that it is much higher and much better. Thus we would conclude that perhaps it would be better to make use of only X2 and rather to disregard X1, as we see that it is not an accurate predictor. This concludes this question. Question 5. Read the success ratios off from the Taylor-Russell table, but you will first need to calculate the base rate and the selection ratio. Alright, so I'm not going to go too much in terms of how these values are calculated or what their interpretation is. I'm only going to be linking this to you guys. So basically this is just a short summary of the Taylor-Russell approach to calculating the return on investment of assessment, which is basically this entire activity that we're doing here. Alright, so you can have a look and read through that just to make sense of the whole thing. However, we're only going to be focusing on the calculations. So, to calculate the base rate, you take the true positives plus the false negatives divided by the total. So, true positives, false negatives divided by the total. We want the selection ratio, which is true positives plus false positives divided by the total. Alright, so now the second part of the question is that we need to read this off of the Taylor-Russell table. So I'm just scrolling this down to the table. Mr. van der Bank just put us in the one that is corresponding to what we need, which is, as we can see here, 0.31, which is very close to 0.3. So we see the selection ratio. Well, we calculated it now, and we see that is 0.2. So we follow here, 0.2. And now we want to look at our R value, which we also did a lot earlier in the exercise up here, which is the correlation between Y1 and X2. You see that it is 0.80, blah, 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 blah. So in reading it off, we have 0.2 for the selection ratio. We have an R of 0.8. And so when we triangulate the two, you see that it has 0.8. Alright, so the value, this 0.8 value, I'm not going to go into too much detail in terms of its interpretation. I will mention, however, that from my reading, it appears as though the 0.8 is significant of how many times the selection procedure is going to produce a candidate that is appropriate for the position. In other words, 80% of the candidates we hire using X2 should be able to give us the performance we need. This concludes this question. Question 6. Redo the scatter plots in step 2 and include the decision outcomes as markers. Alright, so I'll just be straightforward. I did not do this question as it is very difficult to do it in Excel, and although I was somewhat on the right track, I didn't want to confuse you guys too much because it's just basically an aesthetic property of the scatter plot, because as we know from Mr. van der Bank's thing, basically we'll have different colors for the quadrants in which we have points. However, my opinion is that this is mostly an aesthetic thing, and that for an hour and a half exam, or however long we're writing, it's not necessarily worthwhile in my opinion. But if you are interested in seeing how it is done, you're more than welcome to watch Mr. van der Bank's video that he put up in class. Alright, so that's question number 6. Question 7. What do you think would happen if the cutoff score would be increased to 18? Redo step 4 using a cutoff score of 18. Alright, so we're going to basically be doing this over. When we go back to our Excel spreadsheet, we're going to be wanting to put in the cutoff score of 18. So how to do this? We're going to be looking at all these places where we put in the 15 for these two. We're going to be putting in 18, 18, 18, and 18. Doing the same here for this data series. So then basically when we do this, it'll influence the overall quality of our decisions as well as the success ratio. Specifically, we're interested in looking at the difference that would happen or that would occur if we use a cutoff score of 18 in X2. So what we see here is that the overall quality of decisions decreases and the success ratio increases. So what does this mean? Well, when we put in a bit more of a tangible example, so let's say we're now increasing our cutoff score to 18, right? So we're getting rid of the one that says 15 and we're only looking at the 18 one. We see now that the second quadrant and the third quadrant, being our true positives as well as our false positives, decrease in size, which means that our false negatives and our true negatives increase in size. So basically when we're looking at the overall quality of decisions, there is a slight decrease in the overall quality of decisions in that in order to do it, one takes the true positives plus the true negatives. So if this one decreases, then it stands to reason that this one will decrease. However, for the success ratio, in that this is the one where we look at true positives divided by true positives plus false positives, if this quadrant here gets smaller, the one where the people who score above 15 but less than 60,000 the performance, this being our false positive, if it's getting smaller, then it stands to reason that out of all the applicants we're choosing, most of them will be here, here, or here. In other words, we are more likely to have a greater success ratio if our cutoff score is higher. This concludes this question. This brings us to the end of Practical 1 Evaluating Utility, specifically Part 1, Quality of Decisions, Hits and Misses. So just as a short summary, we calculated the correlations between the criterion and two predictors, and then we interpreted them as such. We did up here. For question 2, we created scatter plots for each of the predictors with a reference line on the x-axis to indicate the test as well as on the y-axis. So we did this here and here, and remember when we put in our reference lines, we had to put in another data series for each. Alright, so if you're uncertain at this point as how we do it, please refer to back in the video. Alright, and then we also had to, based on the scatter plot, how effective would you say the current procedure is, compare the two predictors in this regard. Right, so when we look at these two, we saw that, well, the scatter around this one is a lot more than this one, and we ultimately concluded that this one would be our preferred one. Right, then for question number 3, we created categories in the data set representing the FN, TP, FP, and TN. Basically, we did it here, and this little part here. Then for question number 4, we used the following ratios as indicated, so we basically did the calculations for the overall quality of decisions, as well as the success ratio for both x1 and x2. Alright. Then we read the success ratios off from the Taylor-Russell table, just to again refresh your mind as how we did this. So we determined the selection ratio, which was 0.2. We had an R of 0.8. We triangulated the two, and we got 0.8. Alright. Then going back to question number 7, number 6, we concluded that with question number 6 it would be too complicated to include all. Yeah, it was just a bit too complicated for the aesthetic purposes thereof. So I decided not to include that. However, if you are interested in it, there will be tutorials and stuff on YouTube, or you can listen to Mr. Van der Bank's practical in class. And then finally for question number 7, what do you think would happen if the cutoff score would be increased to 18? So we looked at the difference between the two, we ticked this over here, we looked at the difference between the overall quality of decisions and success ratio, trying to also visually plot what the difference would be if we put in this. Alright, this concludes tutorial 1, the first practical session, or the first part. I hope that it had some value to you. Please stand by for the second part to come. Thank you very much.